If you go on Google and search Abacus software student versions, if you search on that ones, and then if you just click on the first one, I will put this link on the chat and download for free. If you just click on this one, download for free. Let me put this one in the, so download for free. Once you click on the download for free, it's going to ask you something. Yeah, you can put your email address and passwords. Otherwise, you can create your account. It is, you can put your student ID if you like. You don't want to put your personal ID, so you can put your student ID and create your account and start downloading this one and install it. So you can work with me, right? So we can solve this kind of an issue. So can you please do these ones? Unmute yourself or put in the chats if you don't know what we are doing. Go on the start downloading. Somehow you need to start downloading, and we're going to install these ones in your computer. Probably 5 to 10 minutes exercise. That's I'm not sure how long it's gonna take, but most of the students, let's start downloading and start installing. If you are watching from your mobiles, probably it is not beneficial for you because we may not be able to install in our mobiles. It is good that if we can just install it in our computer. But if in case you don't have computer, you don't have anything, you are more than welcome to use these softwares in our university. That is able to, you can use this assignment question or this recording, watch it step by step and software. So what we're going to do it this week, I think I need to change this ones. That is would be week 9. So aim of the week 9 is to analyze the plate using the Abacus softwares. The methods that we use in the last couple of last almost 8 weeks, you have a truss. You have truss that's we done using the stiffness methods. We use the beam using the stiffness methods. We done the hand calculations and space case softwares, verifications, and so on. Last 2 weeks, we also done the frame, if you know that stiffness methods. Now we are going to do the plate, which is a 2-dimensional. So like the plates, you can see these plates are kind of thin. I think it would be better to draw in a very thin manner here. So it would be plates would be like this, and let me erase this. Yep. So plate would be like this, where thickness are relatively smaller than other dimensional. Like the thickness would be smaller than other dimensions. Now these plates could be used in for civil engineers. It could be slab. For manufacturing students, it could be the platform for your machines. For automobile industry, somewhere you manufacturing students can use plate and in a many components or many machineries. So you can use that plate. For electronics, telecommunication students, you can have this circuit board that you can count as a plates and so on. So this is a plate. It can be generalized problems and it can be used for various applications. So things that we're going to do it is applicable for all disciplines, general disciplines. So let's introduce the problems and then we do the analysis using analysis of the plate. Now, as I said, plates are very important structural elements. They may be used as a slab in the buildings or bridge decks. It can be used as a plate for manufacturing students, like plates in the automobile industry, plates in the machineries, plates in many occasions or many applications. The plate you can find for manufacturing students. The circuit board that you come across for telecommunications students and electronic students, those circuit boards can be classified as a plates. Plates are structural elements that bound by two lateral surface. So you can see the lateral surface, meaning that you can have a plates like this, and they have a two lateral surface. So if you want, you can hold these two surface like this lateral surface, and then the load will be applied. Dimension of the lateral surface are very large compared to the thickness of the plate. So you can see these dimensions, which is the lateral surface dimensions. Let's say this is h, is relatively higher than the thickness of the plates, like the thickness of the plate is t. A plate may be thought of a two-dimensional equivalent of the beam. So you can consider this one as a beam, but plate would be two-dimensional. Plate are generally load normal to the plane. So how? This is the normal to the plane. So generally the loads coming onto these plates are normal to the plates like this. Analysis of the plates. Okay, now there are various steps that we're going to follow. I will not going to read it. It will be boring for you, but I will straight away show you using the softwares. So if you go on any university or your computer installs, if you type Abacus and then Abacus and then CAE. If you want to take a notes, you can take a notes. That is how you're going to open the softwares in the university computers, or if you have already installed in your laptops, you can open these softwares using this command. That in the search bar, if you put Abacus CAE, it will going to show you the software which are installed. Listen to what we are working on, and we are recording. Students who are following, I think one student is following. So that, okay. Like the screens which I showed to you. If you have any problems, you let me know that if you have any issue. Isa, when you just ready, you just put the yes in your chat so we can move on to the next steps. Okay, so Isa is ready now. So now I think I can introduce to you some of this one. So on here you have file. We're not going to use all the buttons. I'm just making yourself familiar. It's very easy software. Don't be scared of these environments and all. We're not going to use all of these functions. I will show you which ones you need to use it. And as I said, if you have any issue using these softwares, you can call me or you can book an appointment and we will go through it together. But I'm sure you will not face any issue. So there is a file buttons that you can see, all standard save as kind of things, set working directory, import, run script, and so on. Model, viewports, view, parts, shapes, futures, tools, plugin, and help. So but we're not going to use it. I'm just making yourself familiar. Over here as well, there are various buttons that you can, if you stop on, if you just hold on your cursor on that ones, you will see what those buttons are belongs to. If you can't see any of these ones, you can customize. I think let me see if I can customize that one. So I think it's in the tool. If you go on the tool and or view and toolbars. So in here, if you turn it on, so for example, let's say view options. If I turn it off, that view option is gone. And you can turn it on the view options and you can see these view options are coming up. So toolbars, you can let's say color code. So that color code is gone. So you can turn it on and turn it off, anything that you don't want. You can rearrange these tools as well. So there is a 3 dots or 4 dots here. If you hold on that ones, you can move these ones anywhere on these ones, and you can dock it when you finish it. So that is very friendly. You can arrange it the way you like it. You can move any of these toolbars in any position, or you can decorate and we can make it steady. So that is pretty much it. So you can see that you can move it anywhere on this environment. So that's hopefully understand. So we, as I said, we're not going to use all of them, but this is how we solve all these tools. Now here there is a model tree. You can see on the right side parts, material, calibration, section, profile, assembly, step, field output request, history output request, time point, ALE, adaptive mesh control, interactions, and so on. Right. So there are various model trees. So we can work on here as well. There's these things here as well, modules. So you can see there are various modules that we're going to use. There is a part module, there is a property module, there is a assembly module, step module, interaction module, load module, mesh module, optimization, job, and visualization and scratch. So there are various modules given here. That's also be useful. So I will show it to you both ways. We're not going to touch these ones, but that is the models, there is a parts, there is no any parts at the moment. So that is the complete some of the pictures. Here you have models, here you have results. There is no any results at the moment. This is model database, so that is the model database. This is your working environment. I hope it is not too fast. I'm just putting this information for you. Does it mean that the question 2 of the assignment 3 can be done only using abacus? I mean, no hand calculation for question 2. That is correct, Sagar. And there are pretty much small hand calculations that we need to do it in the question number 2, but majority of the question number 2 dedicated to the abacus softwares. Does it answer your question, Sagar? Small hand calculations? Yep, small hand calculation, but majority 90%, 80% work need to be done via abacus software. Is it okay, Sagar? Softwares, you don't need to purchase these softwares, you don't need to pay anyone. These softwares, yep, it's okay. Yeah, I'm providing the information, very simple. You can install it, the link is there. I think the other students are following with me as well, so there is no any issue. And we are recording, so you can watch it later and pause it and develop that models. Very simple models which I'm going to show you. Exactly the similar models will be given in your assignment, so should not have a big issue. Now, so that is all good for here. First thing first, you can click on the parts. Click on the parts and let me follow my lecture notes so we can follow the lecture. So all the details are given here. So let me read the question. Consider the plate shown in the figure. So that is a plate here. Find the deflection at the center of the plate subject to a uniformly distributed order of 1 Newton millimeter. So we need to find the displacements here and the center. So if I have a plate here, like this, these plates is like a square plates, and these plates will deflect like it under this loading. It will deflect like this. It will deflect, and then these center points that you are getting, that we need to find this how much deflection is happening under this load. So there is a clamp here, is fixed. This is simply supported, and simply supported, and thickness is 6 millimeters. This distance A is 1000 millimeters. This distance B is 1000 millimeters. The plate is 1000 millimeter by 1000 millimeter. Thickness is 6 millimeter. Young modulus is 200 gigapascals. Poisson's ratio 0.3. That's the details given here. So step number 1, we're going to create this this part, which is slab S4R. So that's the parts that we're going to create. So you can give any name, by the way. You can give Vipul here, Vipul underscore plate. You can give assignment underscore 3 plate, any name. That name does not matter. You can put your name, whatever, but that names you need to be recognized. Just kind of some identification. This software does not like if you put the space like this. No, it does not like it. You need to have a continuous like without space. Let's say we put the slab. Let's follow the conventions. Slab underscore S underscore S4R. So slab underscore S4R. So something like that. If I put the space, they will not gonna like it. So you need to keep it this space close. Then we can go to our lecture notes. Then we need to put 3D, deformable, cell, and planar. So 3D, deformable, cell, and planars. And we can put 4000s or something. I can show you what is these 4000s meaning. Let me explain you this. That is a 3D. 3D meaning is a 3-dimensional object. 2D planars, if you have very thin 2D, like a very thin, no thickness, then you can have a 2D planar. Axisymmetric meaning that if you have a cylinders or something like this round cylinders, and then you have the symmetric. So if you take a axis, then this has a symmetric. You can see around this rotate is everything is same. So if you have axis and all these materials and boundary conditions are same, then you can have axisymmetric. But our course does not require to go all these options, 2D planar, axisymmetric. We're just going for 3D deformable. If you have a this discrete rigid, meaning that if you have a plates which are very solid, not deforming, like sometimes you make it very rigid plates. Now, if you know that sometimes if you want to deform some components, let's say something you want to make a platform. right? Some very strong platform. So that's you can do it rigid plates, like very strong plates, not deforming plates. Analytical rigids, similar stuffs that if you want to have an analytical rigid plates that you want to mimic, you can do that ones. We're not going to do it any of these ones in your course, so you don't need to worry about it. You keep it all default 3D deformables and cell. Solid meaning that again is a solid elements. We keep it cell because it's a thin layer of is a thin plate, so we like to keep it as a cell. So that's all good. Now approximate size 4000. Just keep in mind these 4000s, what it going to meaning. I will show it to you. So 4000s meaning. Now let's hit the continue button. Now if you use the middle mouse button, scroll it in and scroll it out. You can see scroll it in and scroll it out. That's you can do zoom in and zoom out with your middle mouse button. If you have laptops, I'm not sure without mouse, I'm not sure how you're going to do it, but these softwares, Abacus softwares works very well if you have a mouse. So if you have a mouse handy attached to your laptops, it would be useful to work with the mouse. Now, as I mentioned, seat size is 400. So that is a 00 here. This is a coordinate. I think if you use the AutoCAD or something in your previous undergraduate degree, that would be useful. So 00 here. Now I put 4000, meaning that from this line to this line is 4000, meaning that this is 0. So minus 2000 goes this way and another 2000 goes this way. So total 4000. So that's the seat size that I put it in the previous window. You remember that one right here? It is put 2000 here. It means that you have thousands from this point to this point is 2000 and 0 in the middle. So that's what the meaning of. I put 4000, meaning that you can put that numbers, any numbers that you want to put it, but make sure that you put the numbers, which is because basically we like to draw thousands by thousands, right? So if you put 500 by 500 or 500, if you put 500, then you will not be able to fit these seats into the grid. It will go outside of grid. Nothing wrong if it goes outside, but you want to keep it in within the grid so you can see and visualize that one. So that's all good. I hope you're following. After these ones, you can just draw it up. So we can take these ones, create lines. So if you go on here and create lines rectangles, or you can do this one as well. So let's click on the create line rectangles. Click on these ones and you can see here you will have pick a starting corner of the rectangle. You can pick it or you can put the coordinates. Now to put the coordinates, you with me that we like to draw these ones. We like to draw these ones, meaning that we have 1000 millimeter here. Where these thousands coming from? That's so one here, thousands and thousands. So we like to draw thousands here. We like to have a thousands millimeter here. And by the way, these abacus don't have any units. So we're making sure that if you set the units length in millimeters, that's OK. Keep in mind that your length is in millimeter and you have 1000 millimeter here. And you have 1000 millimeter here. So if you draw the line like a 00 in the middle, then this point would be negative 500. I hope you know this. X is negative 500, positive 500, because this one here would be negative 500, 0. Right? Y is 0. It goes here. And then we have another point here. That would be positive X 500 and negative minus 500. You can put this point as well. There is no any issue. 500, any points that you like it. 500 by 500, or you can put negative 500 to 500. Any point, any two opposite points you can put it. So let's put these two opposite points 500. So let's say 500, 500. Put these ones in here, here, down here. It's asking you pick a starting corner point. You can pick it or you can type it. So I'm just pick the points here by coordinate 500 by 500. Click enter. So that's the point here. Then in the opposite side, you have minus 500, minus 500 and enter. Did you draw it? Minus 500 by 500 and so. Student who are following, did you draw it or did you fall behind? Let me know if you have any questions there. Any questions in drawing these rectangles? What we draw is thousands by thousands millimeters that we draw. Where to keep the coordinates? Where to keep the coordinates? Here, down here. In the bottom left corners here. My cursor is here. Did you enter the coordinates or I show it to you from the start? Did you get this kind of a window? Or I can show it to you. OK, you got it. So that's you pretty much minus 500 by 500 and all. And you can do the middle mouse buttons to exit from these commands. So you can press the middle mouse button that will exit from the command. Sketch the section to the planars. Now we can put the dimensions if you like. If you want to see what dimensions you have, that is not required, by the way, just for your reference. That you can add dimensions. You can click on add dimensions here. There is a button here. You can see somewhere in the middles. There is a add dimensions. Can you please click on add dimensions? And you can see select the entity to the dimensions. Click on these ones. And then you can just scroll it across and you have thousands and press enter. So you can see thousands here. So now you are confident that is 1000 millimeter. If you want to delete something, there is a delete button here. You can click on here and you can delete any of the lines that you did not you draw it very incorrectly. And then again you can click on dimensions, and if you want to see these dimensions, and click on this ones, and you can see this is thousands here showing here. If you're happy with that ones, you can put thousands. If you're not happy, you can change the dimension here as well. You can make it 2000, so it make it 2000. It can goes to that one. So if you want to, let's say, change it here and you make it 2000s, you can see that's 2000s. I think it's not working. If you want to change this, and don't follow these ones, I'm just showing you for your information. 2000, you can see it goes 2000. If you want to change it here as well, you can make it 2000 and it makes it 2000. As you can see, it's expanding. We don't want to do that one. Control Z. So we go back to the 1000 by 1000. So don't follow this one. It's just thousands by thousands. Any questions so far? Any questions to drawing there are various tools. You can draw the circle, you can draw rectangle, you can draw lines, you can draw ellipse, and then you can chamfer it, and there are various options that you can explore here as well. But if you for your assignments, if you know these ones, it's pretty good. There is no any big issue for that. So far so good. Any questions? No, you can hit the done button here, and that's your plate. Right, you can see if you want to see it here in the different configurations, you can move it like this. You can view. If you don't have these ones, you can go here, view and toolbars, and then you can turn off these views. You can see that's gone, and you can turn it back to views. These ones you can move it across anywhere you want to like it. If you want to keep it in the middles, you can keep it here. Right, you can rotate as well. So if you have this button, rotate view, Control Alter MB1. So if you do these ones, you can rotate these into this any direction. So you can see that. So very simple. If you want to keep it any of these ones, you can come back here in the view and you can do it that view as well. Any questions? Any questions? Any comments? So far, so good. Yep. OK, so far so good. So let's continue. I'm going very slow, by the way. Let's put the materials now. If you come back here, there is a material buttons. You can see on this one model tree, you have material button here. or you can do the property here and you can do the material here. That both give you both same things. You can do either click on here materials, or you can go to the module, go to property, and this first one create materials here, or this first one you can create materials. The same windows comes, or you can click here. There are multiple ways to get these windows, right? So option one, you can double click on here and you get materials. You can go in the property here and you can click on this first toolbox and you can create. That is another way to do it. There is a button here that the materials, you can do it here as well. So there are multiple ways that you can do it, the same things, whatever the way you're gonna like it, you can have it. So you can see the slab part number is appearing here. If you expand this ones, there is a slab here as well. So let's click on materials, and the materials, let's say put the steel, it is a steel plate. Again, these names, you can put any names. Your answer will not be affected by what names you putting. You can put material one, material comma steels. You can put material dash steel. Again, it does not like if you put the space. It will not gonna like this ones. Material comma steels. No, it will not gonna like it. The space, they don't like it. What you need to do it, you can put underscore or dash. Then you can put steels, or you can put continuous steel like this. It's up to you, the way you're going to like it. So let's say material steels, or you can say plate material steels, whatever the names that you can fill. And you can, because sometimes if you have different materials, it is good that if you give them a proper name. So these names, that is just for our reference. The model does not require, your answer will not affect it. If someone put material steel, someone put plate material steels, this answer would be same. If someone put the Vipul, that's still same. If you are students and you want to put your names, that's still the answer would not change. It's just the name that you want to put it for conventional. There are various things: general, density, users, materials, user defined field, material, elasticity, plasticity, damage, damping, expansions, and all. There are thermal property, electric. The students who are from our electronics friends and telecommunication, they might like this kind of things. They know this vocabulary, and there are others. So for our course, we are just going to use this mechanical, elastic, and elastic. Click on mechanical, elastic, elastic. So once you click on elastic, elastic one, it will ask you the Young modulus and it asks you the Poisson's ratio. You can keep this one isotropic, don't change it. We don't want to do the user temperature dependent data. We want number of field variable. We don't want to add it. Module time scales for viscosity, long terms, don't change it, and no compression, no tensions. That's OK. We will have the same thing. So we have Young modulus and Poisson's ratio. So now we have given in our examples, we have given 200 gigapascals. That is given in our examples. You can see that this is given here, Young modulus 200 gigapascals. Now let's check the units. Young modulus is given as a 200 gigapascals. Now we have load in the Newton millimeters. As you can see, there is a Newton millimeter. So our load is in Newton. Our load is in newtons and our length is in millimeters, right? We are working on these units. So we need to be consistent with this one because gigapascal does not make sense to me. So what we do it, 200 times 10 raised to power 9 pascals. You with me? Right? Giga means 10 raised to power 9. So we convert this giga, that G, that is like a kilo, is 10 to the power 3, mega is 10 to the power 6, giga is 10 to the power 9. So we have gigapascals. Now, once you have these gigapascals, you have 200 times 10 raised to power 9. 1 pascal is 1 Newton per meter square. Right? So that is 1 pascal. So if you have pascals, I can write as a Newton per meter square. Now we need in the millimeters. You can see that we need it into the millimeters. So if you need it into the millimeters, we can just 200 times 10 raised to power 9 Newton per millimeter square, and we're going to have it thousands for 1000 millimeter equal to 1 meter. So we have 1000. So if you just do this one, so there are 6 10 to the power 3. If you solve these ones, you will get 200,000 Newton per millimeter square. Right? That's what you needed. If you use your calculators and put it in your calculators, you get this 200,000 Newton per millimeter square. That's what we needed, right? So in the abacus, Young modulus, we can put 200 and thousands. You can put these ones, and the abacus don't have unit. As I mentioned, we need to be consistent with the unit. Whatever the length you put, you need to be the unit for this material is to be length. So your load is in the Newton, your length is in the millimeter. You remember that we put 1000 millimeter, right? If you put one by one, then in the meters, so in this one you can put Newton per meter square. So you can put 200 times 10 to the power 9 Newton per meter square. So you need to be consistent. Whatever the numbers you have put in, you need to have a similar units, the same unit. Otherwise, your answer would come up with a different. Your answer would not be correct. So you make sure that your units are consistent. It's not like the space gas where they are saying, OK, I need these units and there is a megapascal or something. Excuse me, they're putting those things. So that is things are not required here. Poisson's ratio is given 0.3. There is no unit. The Poisson's ratio is unitless, so that's no issue. So that is 0.3. What is Poisson's ratio, by the way? Anyone knows? Did you heard about Poisson's ratio? Did you heard about Poisson's ratio? Yes or no? Or this is first time you're hearing Poisson's ratio? Have you heard about Poisson's ratio? You can Google it. What is Poisson's ratio? You don't need to remember. You need to explain me. And I'm not asking definitions like blah, 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 blah equal to this. No, I want you to tell me the explanation that your brother or your sister who are not engineering background, or your uncle, auntie, or grandparents who has no engineering background. If someone walking on the road who has no idea what is engineering, and you try to explain the Poisson's ratio to that one. Lateral strain over longitudinal strain. Perfect, Sagar. Thank you. What does it mean? How do you explain? This is the definition. If you tell your uncle who are not engineering background, or someone who I know your brother, sister, and say that Poisson's ratio equal to lateral strain over longitudinal strain, do they be able to understand? They say, go away, what you talking about? I agree. That is the correct definition. Lateral strain over longitudinal strain. What does it mean? How do you explain? You understand my questions, right? That I want some story. So let me explain you that one student's already talk about that one. So EMS5CAE. So in here, let's say Poisson's ratio. So let's say you have Coca-Cola can. You know Coca-Cola can? You know this, right? Your uncle, auntie, someone can understand. There's aluminum can. Coca. You know that, right? This aluminum can, and there is a lid here, and then you can open it and drink the cold drinks. Now, if you have this can, and let's say you pulling this can from this, you put it in this machine, and these whole things you are pulling. These whole things you are pulling this way, and this whole things you are pulling this way. You with me so far? There are two guys who pulling this Coca-Cola can. It's empty, by the way. There is no Coke inside, so otherwise we're gonna blast. And someone gonna pull these ones. When you pull these ones, what gonna happen to the Coca-Cola can? This will going to reduce the size, and that will going to extend a bit. You with me? That it will going to extend a bit. You with me? That this one happens. You with me? That these things gonna happen. So there are two things happens in here. One thing that these guys from here to here, let's say this is A1, that's become A2. You with me? A1 become A2. Let's say A1 is more than A2, right? Because A2 gonna be smaller. You with me so far? Something happened here as well. Let's say this length from here to here is B2. It's a B1, let's say B1. But that when you apply the load, that's become B2. Do you understand so far? What I'm trying to say? That your Coca-Cola can, someone put it in a machine and I don't have the Coca-Cola can is empty, it will extend and it will squeeze. So these ones, the difference, like how much it going to be squeezed in, like initial was like this ones. Initial can was this one. So this distance here, that's difference. This is your lateral strain. Because whatever the difference, like A2, A1 minus A2, right? That is your this difference. A1 minus A2, that's this how much it's going to get. So that is your lateral strain over how much it's going to extend. This distance. Let's say longitudinal strain. Longitudinal strain. That is your Poisson's ratio. Do you understand these ones? Oh, Sagar, understand. Thank you. So, okay, Sagar, one more question. So, if you have Poisson's ratio of 0.3 and Poisson's ratio, PS, Poisson's ratio of 0.2, what does it tell us? You're saying that I understand the lateral strain versus longitudinal strain. But let's say someone give you this Coca-Cola can that is has a Poisson's ratio 0.3, and someone give you something made of let's say steels or something, and it has a Poisson's ratio or let's say stronger material. Poisson's ratio is 0.2. What does it say? You understand my question? Because someone say that, OK, this is a materials which has Poisson's ratio 0.3. This is a materials Poisson's ratio 0.2. What you're going to do it? You have machines to pull. What do you expect? It will going to, if you have Poisson's ratio 0.3, it will extend more. Or if you have Poisson's ratio 0.2, it will extend less. So if you have Poisson's ratio smaller, the material is stronger, like it will have less strain. You can see this one is proportional to the strain, right? So lateral strain would be less, longitudinal strains would be more if you like, because that is inversely proportional. So you can make up that one. What about the young modulus? Sagar, do you have any or anyone? Young modulus. I don't want you to just plug those numbers. You just think about it, and I will just take this one call from my colleagues. It's just a little bit important. Just think about young modulus. Sorry about this one. It's just how can simply say material can stretch or deform. Yes, so that's kind of thing. Less Poisson's ratio extend less. Yes, how can material be stretched or deform? That's correct. Or that is correct. Yeah. So the young modulus. What do you think about young modulus? Sorry about this. Just a colleague from the laptop. It's not a personal call, by the way. It's just from the university, and I was chasing from them since the morning. So I just need to quickly talk. So sorry for this taking call. Otherwise, I would not take. Now, so what is young modulus, by the way? So is it Poisson's ratio? You answer correctly. It's not a test. I'm just checking whether you understand what is happening on that ones. So the young modulus that you have, what I can explain you the young modulus. Let's say again in mathematical. Yeah, I know that stress over strain. Yeah, that's correct. Stress over strain is a young modulus. I know that one, but as I said, we need the story. Do you understand Poisson's ratio, right, Sakar? Once I explain it, you know those definitions that somehow you remember, or somehow you know from your exams or somehow. But what's the story? What's the statements like? If I say that, let's say question is I have young modulus of 200 gigapascal. Let's say that is steel. That is steel. And I have same materials, young model. Sorry, I have a material with the 20. Sorry, this one is, let me erase that. Let's say this one is 200,000 megapascals, and that is steel. That is steel, 200 megapascal steel. There is another one which is only 20 megapascals, and that is concrete. You can see the difference. All 20, but 200,000 and 20. Right. What does it mean? Like I have E equal to young modulus is equal to 200,000 megapascals, quite high. And another one E equal to 20 megapascals, which is concrete. And you say that stress over strain, that is mathematically. But when I have these two numbers, what does it telling me? That I have young modulus, that is does not tell me where is the strain, where is stress over strain. And I have another young modulus 20 megapascal, which is concrete, and still I have two materials. I have two numbers. What does it tell me? And I take the machine. By the way, I can take the machine. I go in the machines and I have a steel. I have steel and I'm pulling steels. Same load, P, same. And same everything same. And I have same materials, similar, and I'm pulling at the same load. Let's say P. Only difference here is the young modulus is 200 megapascals and young modulus is 20 megapascals. What it gonna do it? Let's say sample one. This is one, which is steel. Two, concrete. Which one gonna extend more? Is it 201 extend more or the 21 extend more? Like I have, I'm pulling one made of steel and it is 200 megapascals. Pull. Same. And let's say red pen. Concrete. And pull. And it's 20 megapascals. Which one gonna extend more? Let's say load is same. It means that steel can hold more compressor or tension load. OK, I understand your concerns. Let's say load is same. Which one gonna more deform? You have steel and you have concrete. The load, you telling me this one. So, okay, let's say load is same. Load comes onto the steel and concrete is same. Who gonna deform more? So steel gonna deform more. Okay, how about we draw these ones? You tell me the definitions. So let's say this is a stress, which is load over area, and this is strain, change in length over these ones. And I have one line, these ones, and the blue line is this ones. Which one is steel and which one is concrete? Blue or red? Yeah, ductile. Young modulus will not gonna tell me whether it's ductile or not, because the Young modulus going to come. That is goes to the stiffness. The ductility does not comes from the Young modulus. It is a stiffness. The initial stiffness come from the Young modulus. So which one? The red one is steel or the blue one is steel? Red might be the steel. Yes, so because you have higher Young modulus, so red one is a steel. And this one is a concrete. Okay, so far so good. So if I apply the same load, which one gonna deform more? Because the steel one going to deform up to here, and concrete will going to deform here. Same load. Same load. This is, by the way, load, because this is load over area, and we can count that the area is same for both. So this is the load that you are applying, both steel and concrete. The steel going to deform up to these ones. This is a steel deformations. This is a concrete deformations. Yeah, so the concrete deform more. You can see that the lower the Young modulus, it has a less ability to resist the deformations, right? To resist the deformations, load would be same. So that will the stiffness that will measure how the Young modulus measures how does the material behave against the load. How much deformations that goes against the load. So if you have a materials and if you are pulling it, if you have higher Young modulus, meaning the material is stiffer, it is stronger to deform, and that's again goes to the deformations as well. So that is a rise overrun, like the stress. If you take this part, which is the stress, difference from this point to this ones, difference from this point to this point. So if you draw it, that stress over strain will give me the Young modulus. Young modulus is equal to stress over strain, the ratio. Let's say this is sigma 2 and sigma 1. You can take the minus of these ones and minus of these ones. Then you will get, let's say, E2 and E1. So that is E2 and E1. Similarly, you can do the rise over run, this stress. You can see this portion is larger than these portions. So in that case, you can have a smaller value. So if you have higher value, this one, it will go smaller, right? So that is the Young modulus. So that's definition is done. So I think no one is following. The students who are following is already gone, I think. All right. Any other questions? Here there are 4 students. No one is following, right? Subham, Sebastian, Santosh, and Sagars. I think you already replied before. You are not following the softwares. Not following. Yep. So that's all good. All these Santosh and Sebastian and Subham and Sagar, they are not following. Okay, so we go a little bit quicker. Quicker meanings we're not going to explain or things, but that's already done, and we're going to hit OK. I think we hit OK. So there is a material here. If you want to change the materials, you can come back. You can double click. You can click here. You can change the material property here. You can property here and hit OK. So this is all good. Right. Any questions so far? Not following. So all good. Any students following? Let me know. Now after this, we can do the section. Again, name does not matter. Again, name does not matter. So sections. We can create slab section S4R. So that's fine. We can put any name section 1 or all. So slab sections. Your answer would not be changed here. Which one you're going to do it? And cell and homogeneous. Like homogeneous material, meaning that the materials throughout these cross sections are same. It's not a composite and not surface and so on. So cell and homogeneous, we create the sections, right? No need to change anything. Just put the cell homogeneous and you put the name whatever you like. Don't leave the space. Otherwise, if I leave the space, look at that. It will give me the error. See, name must be 1 to 13 character long, must not beginning with number, may not begin or end up with a space. So there is a space here. It will give you the error. So you don't need to put the space. You just need to keep this one's cursor. So hit OK. Now in here, they need the cell thickness. Now the thickness that we're going to put is thickness we're going to put is a 6 millimeters, sorry. So we can put 6 millimeters. Again, we can't type millimeters here. And then 6 millimeters, and then you will have these ones. Just leave it same as default. 6 and 5. Don't change anything. You have only one material, so the materials already selected for these sections. If you have multiple materials, you need to drop down and select, but you have only one material. So material is still, that is correct. We don't need to change anything. Thickness integration 0.5, Simpson. We don't worry about any other things. Just enter 6 here. During the analysis, just skip it and the cell and quantum cell homogeneous and hit OK. So we have a section here. Right. Then we're going to do the section assignments. You can expand this part on the right side and expand on this one. There is a plus sign that you can click on, and then you can do the expansions. Then you can do the section assignments. Uncheck this one. We don't want to create the sets. And then we will do these section assignments and hit done. And slab sections, I think middle of the surface, don't change anything, just whatever the sections you got and hit OK. So that's the green color shows that it has a section assignments. I hope it is clear. Section assignment, everything we make it. So far, so good. Section assignment is done. Now we can do the mesh. You can click on the mesh modules here, or you can go here and you can click on the mesh here. We can do the mesh empty here. Just click on from the right side, and then we can just follow the video, follow the lecture notes. We can go to the mesh controls, like here, mesh controls here, that button, the mesh control button here, mesh control, or you can go here, mesh, and there will be the mesh control button here. So that's appearing here, or directly from here, mesh controls, same thing. Then we can go here. We're going to use chord mesh from the element shape, and for techniques, we're going to use structure. So that's good. We're going to quadratic mesh, and we're going to techniques. We're going to structure mesh, and that's all good. And hit OK. So that is nice green colors here. Nice green colors. Now then we're going to do element type. We can go here and we have element type here. We can click on here, or you can click on element type, assign element type. Both give you the same window. We can go back here, standard linear cell. OK, so we have standard linear, and then we will have cells. So that's all good. Standard element library is standards. Geometric order is linear. Family is cells. So it's like a cell elements. Cells, reduce integration, and S4R. So S4R, reduce integrations, that looks good. And you have cells, quadratic linears and cells. And hit OK. Now that is all good so far. Then we can put the approximate global size. So if you're going to go seed part, we can go to the seed part, or you can do this one here, seed parts. You can do it here, or you can do seed parts. So that will give you the same windows. So you can do seed parts. Now approximate global size 100 milli, it will create 100 by 100. You remember that was 1,000. So if you want to create 50, and if you are using the student version, there is a limit for 1,000 elements. Oh, sorry, 100 elements. So you don't want to go over. For this ones, you can use the course maths. You can put 200 if it is give you limit. But let's say you use 1,100 here. The smaller the mass, the accurate results you get. For here, this case is no problem. But for examples, let's say you have some kind of this kind of profile. Let's say you have this kind of profiles. And in these ones, let's say you divided the mass. The smaller the mass you will gonna get it, you're going to get closer to these surfaces, because these surfaces would become like this straight line, right? And there is a curved surface. So if you make a smaller mass, it will give you the accurate results. The smaller mass will take longer time to compute, because every elements that you're going to do it, the computer will going to work on one element, get the results. Second elements, get the results. Third element, get the results, and then it will sum all these elements. So if you have a 100 elements, it's required to do the 100 calculation for the computer, but your accuracy would be less. If you put the 1,000 elements, like smaller elements, the computer need to do the 1,000 calculations, so it will take longer time. For our subjects, not a big issue, because we're not going to use course maths or I'm talking about if you are going in the industry and using finite element package, we might need to consider. My students working on the research project, if you are coming in the final year students, a final year research project, these students working on the little bit of abacus modeling, they do a lot of investigations and run these models with the different mass size and so on, and they come up with the appropriate mass size, which will be accurate and give you the results in a reasonable time. There is no thumbs rules saying you need to use this mass size. It is engineering decision. It is a user decision based on your capability. What is your requirement? What is your tolerance? Based on that, you can use this mass size. But for our case, we're going to use 100 and we hit OK. So you can see there is 100, 100, 100, 100, 100, 100, 100, 100. We might need to do the partitions, by the way. I think I need to do the partitions. What we can do it, we can do the partition cells. You can see here partition cells. There is no geometry cells to be partitioned, so that's okay. We can do it here. These ones, partition cells using part between 2 points. So that's all good. Select the start points. We can do this start points and finish these points and create partitions. So it will create this line where we're going to make it our points. So let's create these ones and select the faces for the partitions. Let's select all, done, and we're going to use from this point to this point and create partitions. So you have these partitions. Let's check again the element type. Select a region to mass controls, and we have structure mass quad. It has changed, so it is green colors. Element type, done. Standard linear cell and hit OK. So that's all going well. And global mass 100 and hit OK. So that is the mass. And then we can mass the parts. And he's yes. So that is it. This is by 100 by 100. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That means you have 1,000 and you have 100 by 100 millimeters. I hope you understand that. Any questions, by the way, so far? Is it doable? If you have this video with you, yep, it is doable. So if you have this recording, and I'm there to help you, not alone, and I'm throwing you in the dark room. I will be there with you with a torch to help you out. But let me know if you have any question or concerns. All right, so far so good. We are going so far so good in a good part. Now, then we go to the assembly modules. We can go to the assembly modules here in the assembly. And we're going to create the assembly. create the instances and we create the assembly. So let's create the assembly. So just click on here, create instances and hit OK, and we have assembly. Now this assembly, we need to do it. Sometimes we have 2 or 3 parts that we need to assemble. So for that cases, we need these assembly modules to be corrected. Just give me a minute. I will just get the drink bottles and come back in 2-3 minutes. Just get the drink waters. Just stay there. I'm just coming back.
વિપુલ તો ગ્રાફ દેખાડે છે આવું જોવા મળે તને વિપુલ બધું કયું સોફ્ટવેર શીખવાડે એટલે એ બાગેશ એ બાલે રખડે એટલે બંધ કર ને એનો વિપુલ એમ તો અત્યારે કામ કરવા.
All right, everything all right? All right, so now we already got this mess one. Thank you for your patience. I think I just need to drink the water now. So you understand these ones, right? So far so good. We reach up to assembly. That assembly parts done. Now we can just going to put the displacement like age number 1 is simply supported. So we have a simply supported. So you can go back here and that is in the questions where we have a simply supported age number 1. So we can just say this is age number 1, age number 2, age number 3, and this one clamp. We can just keep it. We just keep it these figures handy. Let me erase this. So we can see that what is the simply supported and all. So this one. So okay, so we can keep it like in that format, like in this fashion. So you can see we can keep it like this. Like this, right? That is same like in our lecture note. So like this, we have simply supported, simply supported, simply supported, and clamp. So this one would be simply supported. This one would be simply supported. These ones would be simply supported. And these ones would be clamp, right? So I hope you understand that. So we go to I think the steps that we need to do it before. I think why the steps not coming before? I think I should do the step generally before a boundary condition. Let's do the step before boundary conditions. So this one's all done. This one's all done. So we don't. Yeah, they just generally do the initial step. Therefore, yeah, boundary conditions. But let's do the steps here. Linear protrusions, static linear protrusions. Okay, let's do the steps first. Doesn't matter which sequence you're going to follow, doesn't matter. So let's do the steps. In that ones, you can do the static journals here. Steps 1, you can put the name here, analysis plate, or you can keep it step 1, and then linear perturbations, and you can static linear perturbations and hit continue. So and then hit OK, and that's your step 1s are there. Right, so that is there. So is there anything else? Static now pressures and that's it. So, okay, all good. Now let's move on to the next steps, which is the interactions. We don't need to do it. You can skip that steps. Load. You can come back to the load. You can do boundary conditions and manager here. That you can create here, or you can do the boundary conditions from here. That is again one more. You can click on here. The boundary conditions are here. So there is various ways that you can do it. Boundary conditions create. We can say that let's say give them name age 1. I think the name would not be an issue. Age 1 simply supported. Again, name would be no space and so on. So age 1 simply supported. You can give the name and then you can do the mechanical for category and displacement and rotation and hit continue. You can get this line and this line. Shift key down to select the multiple lines. You can do the shift key down and you do the selection for dot and then hit done. And then I think I did wrong. That's need to change to initials. That was wrong. And age 1 simply supported, and initial, and hit OK. Again, you can click on these two, done. And the displacement. So what is this one's X1 stand for X directions. U1 is displacement in the X direction. So this edge cannot display it in the X direction. 1 stand for X. So you can see X. So this edge cannot go in the X direction. When the load applies, it is holding. U2, I fix it, meaning that this edge cannot go this edge. These points can go, this point can go, but the point on this edge, particular edge, this edge cannot go in the Y directions. And the Z, these points cannot go in the Z direction. So this is simply supported. The rotation is allowed. Rotation about X axis, so those points can rotate. This point can rotate. It can rotate in the X directions. It can rotate in the Y direction. It can rotate in the Y directions. Y direction is here. And it can rotate about the Z axis. So that is a simply supported. Displacement don't allow, rotation allow. That is a simply supported. You know simply supported, right? Like you have done some kind of simply supported like this pin and roller. Like these points here, they cannot go here, they cannot go this way, they cannot go up and down, they cannot come out, but it can rotate. As you can see, it can rotate. So therefore it's a simply supported. So U1, U2, U3, I hope you understand this. Simply supported, the rotation about X, Y, and Z is allowed. Displacement, the point translations not allowed. Hit OK. So that is clear. So that is done, is number 1. Now, what is the another one? We can go back to our questions. We done these ones. These numbers, let's say age number 2, simply supported. We can give them name 1 to 1 or 2 or 3, whatever you like. You can put 2 is 2, this one's 2. So let's say this one 2. So we do same thing here. We're going to create age 2, simply supported, and the displacement and rotations initials. Hit OK and shift key down to select this edge and hit done. So U1, U2, U3. Again, this is simply supported, meaning that the displacements for this edge, X not allowed, Y not allowed, and Z not allowed. But the rotations for this edge about X, Y, and Z is allowed. 1 belongs to X, 2 belongs to Y, 3 belongs to Z, and hit OK. And then third one, we can continue this process. Age 3, simply supported, and I can show it to you here. That is age number 3, simply supported. So shift key down, done. And U1, U2, U3, displacement is not allowed, and rotation in X, Y, Z is allowed. Fourth one is a clamp. Clamp meaning everything is fixed. Go back here, age 4, and is a clamp. So you come back here, done. And the clamp meaning displacements in X, displacement in Y, displacement Z is restricted. Displace rotation about X, Y, Z is restricted. So that is fixed. For examples like this, you have seen the cantilever like this. You have this fixed, meaning these points cannot go up or cannot go down, cannot go left or cannot go round, cannot rotate. So that is a fix. So that is the fix. You can see the symbols. These orange colors are for the, so there are orange colors. You can see these orange colors are saying this is fixed in X, fixed in Y, fixed in Z displacements. These blue colors represent there is a rotational fix, rotational fix in the X, Y, and Z. So that symbols also reflect that. So that's pretty much done. Now we can apply the load, and that is the last steps. H4 we done, and then we're going to apply this UDL load, uniformly pressures. Newton per millimeter square 1. So let's apply these pressures UDL, and we're going to do it under pressure, under load. So you come back here, load, create, and let's put pressure or something. And step 1, and we put pressures, continuous, and shift key down. We can select all these steps, and then we will have this. Let's say you want to apply on here. So we can have a brown colors. There is a purple color down. So let's apply it on the brown color. So you can select brown, and we put -1. Then it will goes opposite to Z. Oh, so we can put positive ones. So it can go like this. OK, so that's perfect. You can see this way. You can see this way. Right. So that is age number 1, age number 2, age number 3, all simply supported. This one is fixed. Right. So that is all good so far. Then we just going to create the analysis, and then we will submit. So let's last steps. Load. And then you go to the mesh we already done. So that's good. Job. And we're going to create. Let's say job number 1, or you can give the name that you like. Don't change anything, just keep it here. OK, and just hit the submit button. And you might get this one. You can override. Yes, you can override. And let's wait for, in case if there is any error or anything, we can fix it. But I think there is not any much. Yeah, it's submitting, running. You can hit monitors and see if it is running. Yep, status is running. And completed. So that's good. It is completed. You can check the results. And if you want to see the deformations, you can see the stresses. You can check the U3 deformations. As you can see, there is a, and that's are in the millimeters. You can also create the like this kind of a movie where you can slow it down or faster. Yep, so you can see that. Yep, so you can do the fastest. You can download these movies and show it to the show it in your presentations and all. So you can see that how the deformations are happening. You can do it here as well. You can do it like with your cursors as well, and you can automate that one. So that is the displacements that we want to find. That's the middle of the points. You can see that in the middle of the points. That's what we're trying to find here in the middle. Right? That's what the questions that they are asking. Now we done all these ones. We can try to do it all these steps. So this one is done. Now node and element label. Expand the tree under the job, and then right click on this one, completed, then click on results. OK, that's good. Click on common options. So there is a common option. So we got these common options. So here you can click common options. Then a common option icon, display the common plot options. So there is a common plot options dialog box. Under the labels, check the show element labels. So under the labels, where is it? Under the labels, show element labels. So there is a colors for this one. If you want to change the colors, you can change the colors for element labels. And show the node labels to display the element node numbering. Increase the font size by clicking on the send front all the models, set size 18 and bold this ones. OK, yeah, if you can't read it, you can say the node labeling. And where do we check the font? Set the font for all models labels. That windows appear. You can have it 18 bold and hit OK and apply, and you can see the node numbering. So I think the node number 2 that we are looking for. That is the, because we need to know what node numbers we are looking for the displacement. You remember the questions? That question was to find something in the middle. So that's we plot deformations we done. and U3 be done. Now create the text files. This is very important. So we need to create the text files. Now to create the text report containing the nodal displacements in the menu bar, click on the report and fill the output. Okay. On the menu bar, click on the report and fill the output. So that windows will appear. Then variable unique nodals. Variable unique nodals. Then you can have a displacements. You can click U3. That's the displacements that we in the Z directions we are looking for. Is it in the Z direction or which directions we are going in? Let me roll it. Yeah, about Z directions. You can see this is Z direction. So that's U3 is Z. If you are looking for, if this one is X or Y, you can accordingly select this U3 and then setup. We can have a plate. So setup. We uncheck this ones and we can put plate. You can put any names that you want to do it. If you want to select, it goes in a default temp because that is your working directory. If you go file, set working directory, it will goes by default C simula temp. By default, it can go here, but you can select to not go there, or you can select where you want to do it. So C drive temp right now it's going. So by default, that's OK. Hit OK and override, and that's all good. Now we can get that that report. So node number 61. I think we have node number 2. So we go here in the C drive. We can go to C drive. We can go to Simula. We can go to temp. And yeah, plate RPT. So we can open with the notepad. And there you go. That is your numbers that you're looking for. Displacement 704 minus 704.7072. So you got, yeah, almost same, minus 704 point. Where is it? Notepad minus 700.072. 0.072. That's what we found. Minus meaning that is opposite to that one. So there is nothing wrong with that one. Now in your assignments and everywhere, we have to calculate non-dimensional deflections using these equations, where W cap equal to 100 times D times W over QA4, where Q is a UDL load intensity Newton per millimeters. That's we substitute, right? W is vertical displacement plate centers. That's we calculated. And A is the width of the plate. And then we can substitute all these ones and we find these values that's here. So let's do this one's calculation. So the W cap equal to 100 D small w over Q A4. Now in these ones, we can calculate the capital D as well first. Capital D equal to E H cube. I think you need to do these calculations in your assignment. Sagar asked me that do we need to do the calculation or not? This is the small calculations that you need to do it in your assignments, not big calculations by hand. You have enough done the calculation for by hand. So here Young modulus is 200. I think is given in our examples. 200 Newton per millimeter square. We're working on the Newton millimeter square times by the height is the thickness. So if you look at that height, which is 6 millimeters, H is given in our examples. Here you go, 6 millimeter H. So that H is 6 millimeters. So then 6 cubed millimeter cubed as well here over 12 times 1 minus Poisson's ratio is 0.3 square. Poisson's ratio given in our example 0.3. Poisson's ratio is given 0.3. Poisson's ratio is given. So if you solve these ones using the calculators, you might get, let me put in my calculators. And I'm taking the answers from that. 200,000 times by 6 to the power 3 divided by 12 times 1 minus 0.3 square. You get 3,956,043.956. So that's you get D. Now you can do it 100 times by D. We calculated. It's big number 3,956. That's we just calculated here. 043.956 times by W. I think the W was vertical deflection at the plate centers. And that W we calculated these ones. I think that W was here. Number 2, 704,072. We don't need to take it negative. 704.072. That is W over Q was 1. Let me erase that one. Q was 1. And that is W cap. Q was 1 Newton per millimeter square. Let me put the units, by the way. So Q was 1 Newton per millimeter square times by this A. Now the A distance is given here, and that A was 1,000. So you can do this one. 1,000 millimeter. So this one times 100 times by 704.72 divided by 1 times 1,000. You get that 1,000 to the power 4 divided by 1,000 divided by 1,000 divided by 1,000. So you get 0.1278, right? So that is the value that you're going to get, and you can use this one in your assignments. That value, that tables that you have given, right? Almost there.